Good morning, good afternoon, good evening, wherever you are. Welcome to this SEGGER webinar on streaming and instruction trace and real-time code coverage and code profiling on ARM Cortex microcontrollers. I'm Axel Wolf, and I'm SEGGER's FAE for the West Coast of the United States, located in the California Bay Area. If you have questions during the webinar, please type them into the questions box and we will address them either during the webinar or in the Q&A session at the end. So let's get started. So here's the agenda for the webinar for the next hour or so. I'm just going to do a really quick introduction of SEGGER as a company for those out there who are not that familiar with us. But I promise to make it really quick. Then we'll just talk about basic versus advanced embedded debugging for a little bit, just introduce some terms. So for example, we'll actually talk about what streaming instruction trace is. What do I mean by that? Same for real-time code coverage, real-time code profiling. What is that, and how does it work, and how can it help you? After that, I will do a live demo of JTrace Pro, which is our trace probe, and Ozone, which is our debugger. So to show you those concepts in action. And then after that, we'll just talk about a quick 5 minutes or so about some other advanced debugging features that you can utilize and that can help you in your software development and software debugging. And then we'll have a quick summary, and then the Q&A, some room at the end. But hopefully my colleagues who are on, they should be able to take care of questions that come in during the webinar. So just type them in the questions box and we'll take care of them. So just real quick about SEGGER. We're a global development tools company. We've been around for over 25 years. It's actually 28 years now. And we have offices all around the world. The headquarters are over in Germany, near Düsseldorf, in a city called Monheim. We also have offices in Boston, in the Boston area, on the East Coast, and then in Silicon Valley, where I'm located over in California. And we also just recently opened up our China office in Shanghai. And these are the four pillars of all of that SEGGER does. So we do embedded software. That is all the software that runs on the microcontroller. And I'll give you some examples in the next slide. We do debug probes. We're very well known for our J-Link debug probe, which is the de facto standard in the embedded world for debugging. We also have a line of production tools. Those are our flasher programmers. And we also have software tools to help you actually develop the software or your application. We have Embedded Studio. This is our IDE. Ozone, which is our debugger, which we're talking about today. And then also things like System View, App Wizard. So we have a bunch of software tools that are very helpful too. So in terms of the embedded software, we really can offer you anything that needs to run on the MCU. So for example, you might need a real-time operating system in an embedded application today. You might want to have a real-time operating system, so we have MBOS. You might need a file system. We offer all kinds of stacks and utilities and libraries that are required for networking. Obviously, in these days where a lot of IoT devices are out there need to be connected, we offer all that connectivity. We have USB device and USB host stacks. That's also, of course, still very important. We also support other bus systems, for example, Modbus. Security is obviously also a very, very important topic. So we have mSecure, that's our digital signature suite, and mCrypt is our cryptographic library. And then you might also need a bootloader running on your device. So we offer mload for that, and we have mcompress, which allows to compress embedded software. And obviously, also graphics is an important topic. So we have mwin, which is our graphics library, to drive all kinds of panels. And then, like I mentioned, on the host computer, you might have tools like Embedded Studio, Ozone, System View. So those are embedded software tools. Okay, so now let's get into the topic. So basic versus advanced embedded debugging. So if we just look at a typical basic debug setup, you usually have some computer or workstation with your favorite OS on it, either Windows or Mac or Linux, and maybe you do command line, but maybe you have an IDE and a debugger running on it. And then usually that's connected to a debug probe that's sitting on your desk, and then that is usually connected to your target board. And usually that is done through SWD or JTAG protocols. So there's a debug header, you plug in your debug probe, and then that communicates with the MCU under test. And that usually gives you the basic debugging features. And what I mean by that is you can usually download and run your code from the debugger on the host down to the MCU. You can halt and resume your code execution. You can single step through your code. You can set some breakpoints. So those are fairly basic debugging features that are out there. But there are situations where basic debugging is just not enough. So sometimes you get these spurious or infrequent bugs that are really hard to reproduce and hard to track down. Sometimes you might find that your application is running into a hard fault, and you might not know why that is, and you don't really know why it's happening. So that can be really frustrating. You might have, over the development of your application, you might develop some code that ends up being dead code that's unreachable, that's really not used anymore, but it's not always easy to determine that. And then also there's other parts of your code that are, I would call hotspots, that get executed a lot, and that could potentially, if optimized, could save you or could speed up your system and make it more efficient, and you could have room bandwidth for other features. So for that functionality, you need some kind of trace functionality over just the regular debug, and basically you need some mechanism where you're recording the instructions that are executed by the MCU that enables to do all this. And this is basically where the advanced debugging is coming in. So instruction tracing is the key to do some more advanced debugging, and that is essentially a non-intrusive way of capturing the execution or whatever the MCU executes. But there's different types or mechanisms of instruction tracing that I'm just going to go through real quick, because it's not all created equal. So you might do that through a trace, a data buffer that's a trace buffer that's on the actual MCU, or you can have the trace data being output over special pins that are dedicated on the debug interface. So those are two mechanisms. But even then, if you output the trace information, there's still a difference. You could store the trace information on the probe, or you can actually stream it directly to the debugger on your host. And so we'll talk about some of these mechanisms now. So this is the instruction tracing if you're using an on-chip trace buffer. And they might be called different things in the ARM world. You might find your microcontroller has an ETB, an embedded trace buffer, or MTB, micro trace buffer, or it might be called embedded trace FIFO. So those are usually RAM buffers that are on the MCU to capture trace information. So when the MCU is running, the instruction history is stored in that trace buffer. And then when the MCU is halted, the debug probe essentially reads out that buffer and transfers that content over to the debugger on the host, and then that gets analyzed by the debugger. Now, the drawbacks of that solution is that since the trace buffer is on the chip, it's usually very small. So we're talking a few kilobytes maybe. And it's also a ring buffer. So essentially, that only gives you a very limited instruction history, given how fast these MCUs are and how many instructions they execute every second. There's only a very limited window of history that you can build in such a small trace buffer. So the next step up is basically moving the trace buffer onto the trace probe. So some MCUs, they output the trace information on dedicated debug pins. So you have, in addition to SWD and JTAG, you have dedicated trace and trace data and trace clock pins. And so in Cortex-M and Cortex-R micros, that's usually called the embedded trace macro cell or ETM. And if you have a Cortex-A controller, that is usually called PTM or program trace macro cell. So what happens there is while the MCU is running, the trace data is output through those pins and sent over to the trace probe, and then the probe stores that information into its own buffer. So we're getting the information closer to where we actually need it off of the MCU in real time. And then when the MCU is halted, then basically the debugger reads the trace buffer from the trace probe and then presents it to the user for analysis or debugging. So obviously on the trace probe, we can have larger buffer size. So we can have megabytes or even gigabytes of storage there compared to the kilobytes that we have on the MCU. The disadvantage is obviously that you need some additional pins that need to be part of the debug interface, a minimum of 2 and maximum of 5 extra pins. But usually the extra visibility is worth having to route those extra pins. So then the third solution, or the third option, is really to use a streaming trace probe. For example, that's the category that our JTrace Pro is in. So now you have, instead of just a regular USB connection to your host, you would have a USB 3.0 or even or a gigabit Ethernet connection. So really, really fast. And so what that allows this probe to do is basically, while the CPU is running, you pass the instruction trace data to the host in real time. So now there's no more buffering on either the MCU or the probe. It goes in real time straight to your host computer. And so now, essentially, instead of just megabytes or gigabytes, we're talking potentially terabytes of trace data that you can store. And that is really what allows tracing of instructions over large extended periods of time, essentially possibly from when you start up your system until you shut it down, to trace the whole life cycle of, let's say, a user interaction with your application. And because some of these bugs, they only happen so sporadically that with a smaller buffer size, you might not capture them. But with a streaming trace probe, you can capture so much trace information that you should be able to catch those really tricky bugs. And obviously, having the streaming instruction trace also enables some other nice debugging features that we're going to cover now. So, for example, the real-time code coverage and real-time code profiling. So, let's define those terms. What does that mean? So, code coverage asks basically which parts of the code have been executed. So essentially with code coverage, we look at how much of each source line or block of code or function or file actually has been executed. And so basically you can use that to find code in your application or in your project that's not covered by any tests. And that has the potential for problems later when the code is deployed, and also it takes up memory space that could be used better. So it also detects unreachable code. Again, that's code that should be trimmed and should not be part of your final distribution. So it really helps improve the code, and you can create a suitable test suite to find uncovered blocks. Because really, the saying goes, only tested code is finished code. So if you haven't really tested it, you can't really consider it finished. So there's a little animation here that shows how that works. So basically, while the application is running, you will see the code coverage information and code profiling information come in. And we'll see that again much better later in the live demo. So just take a look at the code profiling window in a little more detail. So you have columns here. This column has all your source code. You have different files usually that are part of your application. We have 2 assembly files here, and then a trace-demo.c C file. And then the next column here is your source coverage. So that shows how much of the source code has been executed. And then the next column, the instruction coverage, is how much on assembly level, on instruction level, how much of your code has been executed. So here you can basically we can open up a certain file like trace-demo.c, and we can see which functions are in there. So we can break it down by function. In this case, we have about 1, 2, 3, 4, 5, 6 functions in here, and you can then further break it down by each function. You can open that up and you can see the individual source code lines, and then even further you can drill into the source code and see the individual assembly instructions. And then for basically each of these source code lines and instructions, you can see what the exact coverage is. So for example, for the whole function itself, the top line here, we can see 66.7% of that function has been covered, and that is 4 out of 6 lines of code. And then on the assembly level, that would be 81.2%, or 13 out of 16 instructions. And for example, for this if statement here, we can see that there's no code coverage on the source level, and on the instruction level, it's 75% because 3 out of the 4 instructions have been executed. So it gives you really good visibility about your code coverage. And then you notice there's these shadings here, some green, some orange, and some white. So that essentially tells you, the color scheme tells you what those percentages are. So the green portions are the percentage of your code that's fully covered. So there's really usually little or no potential for optimization there because you obviously need that code. The orange is the percentage of instructions that are partially covered. So that's something you might want to look at, and that could be good optimization potential. And then the white percentage are those percentage of source lines or instructions that are not covered at all. So those could actually be potential candidates for actually removing. Because if they're never ever reached and you're running through a whole test suite, then why have them in your code? So then code profiling asks the question of how often a certain piece of code has been executed. So with when we do code profiling, we measure the execution time and the frequency of functions, blocks, and instructions. So that really shows you where the MCU is spending all its time. And so basically that lets you optimize, that lets you find those hotspots where for code that is executed a lot and also places a high load on the system. So when you run the code profiling, you will see you get the run counts for the different functions and also the load, and you can uncheck certain functions to see the load over the other functions. But that's just a teaser here. We'll see that again very well in the demo in just a little bit. So also very useful are these execution counters that Ozone has in the source window. So for every line of code in your source, when you look at it, you will see how often it's been executed. And so, for example, for this if statement here, it's been executed 126 times, and then we can drill down into the individual assembly instructions, and we can see the load and the compare have been executed all the time, but this branch here never got executed. So you can tell by the color coding here again. So if you have a line that is orange and green in the source, that means all instructions of the source line were fetched, and at least one conditional instruction of the source line was never executed. So that would be this branch here. And on the assembly level, you can see that this conditional instruction was never executed. And then also, Ozone offers those execution profiles. So if you hover with your mouse over any line of code, you get this execution profile. So for this particular line, we can see it was fetched 126 times, but this instruction was never executed. So it was executed 0 times and not executed 126 times. And then essentially there's other coding, color coding for other cases that you would find in the user guide. So I just highlighted a couple of them. So the other cool thing is that you can then export these code coverage and code profiling into reports. So it can be analyzed further later on by external tools, or actually you can do that as a human readable text. So you can store that with your QA process or for certification of your application. And another nice feature that the instruction tracing allows is the code timeline in Ozone. So this is basically a graphical representation of the call stack over time. And this is also based on the recorded trace data, and then it's mapped to the respective source function information. So you can exactly see how everything is stacking up in your application and what the timing is. And again, I'll show you that in the live demo. So you can see, how long a certain function took, or which subroutines have actually been called, or which RTOS tasks are being executed. Okay, so let's move on into the live demo. So the little target hardware board that I'm going to run this on is one of our trace reference boards. Those are very simple boards that are great for just focusing on trace. So this one has a Cortex-M 4. It's got just a couple of LEDs for some visual feedback, and then here's the debug header with the trace pins. We also have a couple of other boards, one for the NXP RT1050 and then one for an STM32H7. So this is a Cortex-M7, if that's closer to your target hardware. So my hardware setup, that's sitting here on my desk. I have my JTrace Pro, and that's connected through USB 3.0 to my host computer, which is running Ozone. And then I'm connected to my target board through this ribbon cable. And so that gives me my debug information, my trace information, and also I'm actually powering this board through my JTrace, so I don't have any additional power to the board here. And you don't need any special code, so there's no instrumentation necessary or any special project configuration. This is all non-intrusive and easy to set up. So just as a note here, in addition, or instead of the USB 3.0, you can also hook up the JTrace Pro over the Gigabit Ethernet interface if that's more suitable for your environment. So now we can actually switch over to Ozone. Let me bring up our Ozone debugger. So you should see that here. Let me just give you a quick orientation of what we're looking at. So in the center here, the center window is our code viewer. So you have access to all your source code. On the left here is the instruction trace window. So that's where the instruction trace history will be shown. Below that, there's the code profiling window. So that's for our code coverage and code profiling. Our timeline is down here. And then on the right, we have some other debug windows. And that's only a selection. There's more views in Ozone that you can bring up. So our little test application has 2 tasks. We're starting a high priority task and a low priority task for the operating system, and they're just being called, or they're executing in various different intervals. And then in each of the tasks, we are also incrementing a counter that we can later use for data sampling that I'll show you. And let's just take a look at our trace settings real quick. So here are the trace settings that are associated with the instruction trace. We're using the trace pins at this frequency. You can set the maximum instruction count you want to trace, and we're using the default timing. So that's all good. So now we can actually start a debug session. So we can download and reset the program. And what we see is happening is we're actually starting up and sitting at main function. So we've gone through the assembly startup code, and we are sitting at main. And you can actually see that we have already started tracing instructions. So this is essentially the device going through the assembly startup code until it reaches main. And we've also started to populate our code profiling and code coverage information, as you can see here. So here's some source and instruction coverage and some loading, but obviously this is still very preliminary since we just made it to main. And then down here in the timeline, let me show you, we can zoom in here. So this shows you in a graphical way what happened so far. We've been executing the reset handler, and essentially we just made it to main. That's where we're sitting right now. So this is a nice graphical way of seeing what's going on. So now we can start single stepping through our code. So just step over the current function, and we can see how after every step, basically the instruction trays and the code profile and the timeline, they get updated. And we can see how our code execution is progressing. So we can see all sorts of things are happening. So that is good. We can keep stepping. And at some point, we will just be, after all the tasks have been created. Yeah, so over here is my MBOSS RTOS window, so I can actually see which tasks in my operating system are have been created and what their status is and their stack information, the priority, how often they've run and such. So that's good information as well. So at some point we'll be running freely, and I can just show you real quick. So this is a live shot of my desk here. So the LEDs are just running. They're just blinking based on the execution of the high priority and low priority tasks. And we can see the live code coverage and code profiling information coming in. So you can sort that basically by source coverage. That gives you a nice view of which functions have been covered 100% and which ones only partially, both on source level as well as instruction level. We can sort it by run count, so we can see which parts of the code are executed the most. In our case, this is just the idle function. And obviously that also places the highest load on the MCU. So that's why it's so handy to just be able to untick that. If I don't care about this right now, I can just see where else, which other functions have the highest load in my system. And obviously those are running a lot. And I can basically, that would give me a potential to optimize those for the system to run smoother. Okay, so then over here in the source window, we see our execution counters. So those also go up in real time. So we can see how our tasks are being executed here. And again, we can do that on C code level as well as assembly code level for each instruction. But obviously you also have, in the disassembly window here, you can also see that live happening on assembly level. So the counters are counting up over here as well. And then, as I mentioned in the intro, if I'm hovering over each line, I can get the execution profile for each and every line in real time while my code is actually running. Okay, so now we can actually, let's set a breakpoint in one of these tasks. So for example, in the high priority task, I'll set the breakpoint here, and then obviously, as soon as the breakpoint is hit, everything stops and all the windows get updated. So here I have my instruction trace, and I can see exactly what happened before the breakpoint was hit, which sometimes you set breakpoints and you hit them and you shouldn't be hitting them and you don't know how they got there, how you got there. And so it's very, very useful to be able to step back in the instruction trace history and see what was actually happening exactly before you hit the breakpoint. So I can move up in my instruction history, and you also see that that is synchronized with my source window and my disassembly window and my timeline window. So as I'm stepping through here, I can see exactly what happened before I hit the breakpoint, and that can give me important clues as to what if the breakpoint was executed, or if I shouldn't have happened to reach that breakpoint, what led up to that. Okay, so that is very useful. And then also you can see in the instruction trace, you have it as on assembly level, but then also over here, here's the function on C level. So I can also go through it on a function or even file level. And then, as I mentioned, I can export that information into a report. It could be CSV or just a human readable report. And then that would be basically looking like this, where you have the code coverage summary here and the code profiling information here, and you can store that report with your application with your tests, and also submit that for certification if you need to. So that is very useful. So let's get back to here. So another nice thing that the real-time tracing enables is data sampling real-time. So we can actually look at these counters while they're running in real time. And if we just remove the breakpoint and start that up again and add the data here, we can see these counters, how they go up in real time and are being reset when they reach 100. Let's give those some different colors. So we can see that happening in real time, and we can also, when we halt the information or the execution, we can then we get the history of our executed code, and we can correlate the code execution and our timers going up. So you can see the task switches here, and we can see the timers going up here. So we pretty much know that this block of code here is responsible for the timer, the timers being, or the counters being incremented. And we can see that, yeah, we execute our high priority task and our low priority task, and then we go back to idle. And of course, we know the counters are incremented in both of these tasks. So this is the effect that we're seeing here. Since I'm actually powering the board through JTrace, I can also do power sampling on top of that, also correlated in the timeline. So I can actually activate my power sampling and then also activate that here. And so now I'm going to get a, when I restart it, I'm going to get a correlation between my code and my power consumption, which then also gives you good visibility into, if you suddenly have a big spike in power consumption, you might want to look at that piece of code and see if that is correct. And you can see the types of code that use the most power. So if I start that back up again, I can see my code execution here. And so that gives me my power profile now. And basically, this goes hand in hand with whichever LEDs are on. So if both LEDs are on, I'm using about 66 milliamps. If both are off, I'm using about 55 milliamps. And again, I can look into my code history and I can see, so this jump here in current consumption must be related to this task switch here. And again, yeah, we can see we're going from idle to the high priority task, which turns on one LED, and then right afterwards, the low priority task turns on the other LED, and that basically is responsible for this increase in current consumption here. So just hope to give you a nice quick introduction or live overview about these different features and how they can help you with your debugging process. So let's go back to PowerPoint real quick to wrap it up. So let's just talk about some other advanced debug features, some of which I've actually shown you. So for example, the RTOS awareness in Ozone is nice because you can in that RTOS view you can see the different RTOS tasks that are happening or that are have been started and what their priorities are, their names, how much stack they're using, which is extremely helpful to determine because it's always hard to say how much stack does my task really need. You don't want to assign too much RAM to it because it's precious, but you also don't want to get any stack overflows, obviously. So it's good to see how much is used and how much has been allocated, what the status is, how often it runs and such. So all that information is visible. If you're using a different RTOS, not our own, we have a JavaScript interface that allows you to actually create that RTOS awareness for any other OS. Or you could contact us and maybe we could implement that for you. Power trace that I showed you, so that allows you to correlate the data sampling with the current consumption and the program execution. So this is basically what we did in the demo. You can see the correlation here. And also, if you want to see that again in a different video, we have one under this link. By the way, we will send out a link after the webinar, most likely tomorrow, and you will be able to rewatch the webinar offline. So also, this is the target exception dialog. So I mentioned sometimes you might run into a fault, some kind of a hard fault, and the target execution just stops, but you don't really know why. And so basically Ozone debugger and with this instruction target exception dialog will show you the exact status of the exception registers, and it will give you a reason for why you just suddenly stopped. So that can be really, really helpful to figure out why that's happening and make it stop. So we also have 2 dedicated videos on that topic on our YouTube channel. So check that out if you have a chance. Also a nice advanced debug feature is conditional code and data breakpoints. So, I mean, setting a breakpoint is nice, but sometimes you only want that code breakpoint to hit under certain conditions. And so you can actually fine-tune the breakpoints and basically turn them into complex breakpoints, which, again, only under very specific conditions that breakpoint gets hit and it gets bypassed if those conditions are not met. And then in addition to code breakpoints, Ozone also offers data breakpoints. So you can watch data locations or variables and accesses, read and write accesses to them. And basically, for example, only when that particular memory address or variable is being read or written or accessed, then you hit a breakpoint. So that is also very, very useful sometimes. If you get a memory location that gets clobbered, you can set a breakpoint on that, and then you can, with the instruction history, you can figure out what happened there. And then the last one I want to mention is that's a separate tool here that we have called System View. That's our real-time analyzer and recorder tool. That is a topic for a whole other webinar in itself for a later date, but System View is a very helpful tool for real-time recording of your embedded system, and it captures all the interrupts, timers, tasks, API calls, and everything, and makes it nice, and it puts it in a nice visual representation while the application is running. And so you can do live analysis and visualization of the captured data. So if you're interested in that, check out System View on the SEGGER website. So that brings us to our summary. I hope you saw how with the JTrace Pro trace probe and the Ozone debugger, you We can do streaming trace as well as real-time code coverage, real-time code profiling. We learned about the different mechanisms of instruction trace and that they're not all created equal. It really depends on the real mechanism on how the instruction trace information is being basically transferred from the source, which is the MCU, to the debugger where you need it to be analyzed. And essentially, upgrading to advanced debugging, it takes a little bit of an investment, but that usually pays back by itself very, very quickly. So in the end, it will save you time, it will save you money, and it will save you and your team and your embedded engineers a lot of frustration if they have the right tools to track down those hard to find bugs more quickly. So that those things usually pay for themselves. So before we get to the Q&A, or before we close, just some additional resources you can access. So obviously you can visit our website. We have a dedicated landing page for Ray Trace as well as for Ozone. So you'll find helpful information there on some of these topics that we covered and more, because we only had so much time. Like I mentioned, there's also a variety of videos that you can watch from our library. So those you can watch directly on our website, or you can go to our SEGGER YouTube channel and watch them there. And then obviously we, for all of our products, we have pretty nice user guides and user manuals that you can check out for more information. So with that, I thank you very much for attending, and we will see if we have any additional Q&As that we have not yet covered. Let me see in the questions window. Yeah, so I think most questions have been answered, so that is very good. Thank you very much to my colleagues, Shane and Nino, for backing me up while I was presenting. Again, thank you very much for attending this webinar. I hope you found it useful. Leave us some comments or feedback in the survey that pops up when you finally leave the webinar. Thank you so much. Have a good rest of your day and stay safe. Thank you.